Welcome to a new portfolio management topic on the measurement and management of market risk. In this first lesson, we examine value at risk as a measure of portfolio risk. We'll learn the definition of VaR, followed by the methods to estimate VaR, namely the parametric method, historical simulation method, and Monte Carlo simulation method. Let's get started. Value at risk measures the downside risk of a portfolio. There are three components to describe value at risk: the minimum loss, the probability of incurring the minimum loss, and the time horizon. For instance, the statement, "The portfolio's monthly 5% VaR is $2 million," means that there is a 5% probability that the portfolio will sustain a minimum of $2 million loss in any given month. The minimum loss may be expressed as an absolute amount or as a percentage. For example, if the portfolio value is $100 million, we can say that the portfolio's monthly 5% VaR is 2%. Be very clear that the percentage attached to the VaR is the probability, so the other percentage must be the minimum loss. We can illustrate this in the form of a probability distribution, plotting the frequency of monthly returns of the portfolio. The area under the left tail represents the VaR. 5% VaR indicates that the area under the left of the minimum loss is 5%. VaR is typically expressed for 1%, 5%, or 16% probability, which is one standard deviation below the mean for a normal distribution. The time frame specified also varies. We could estimate VaR for a day, a week, a month, or any other relevant period. VaR can also be expressed as its complement. For this case, we can say that there is a 95% level of confidence that the portfolio will experience a loss of no more than 2% in any given month. In estimating VaR, an analyst first sets the time horizon she is interested in. She can either fix the probability and estimate the corresponding minimum loss, or fix the minimum loss and estimate the corresponding probability. There are three key methods to estimate the VaR of a portfolio: the parametric method, historical simulation method, and Monte Carlo simulation method. Regardless of the method used, the first step of every VaR calculation is to identify the set of risk factors that affect the portfolio return, a process called risk decomposition. Each security in the portfolio can be regarded as a risk factor, and each security may be affected by a number of risks, like market risk, interest rate risk, or currency risk. So for a typical portfolio, there could be many risk factors to consider. The second step is to gather a data history for each of the risk factors. The period used for this historical data set is called the look-back period. The third step is to estimate the VaR based on the historical data, and this is where the three methods differ in approach. For simplicity, we shall just consider a portfolio that consists of just two stocks over a look-back period of 10 years of annual returns. The return of both stocks are assumed to be affected by only market risk, so we have only two risk factors to consider, one for each stock. The parametric method usually assumes that the risk factors are normally distributed. This allows us to estimate the risk of the portfolio based on the means, variances, and covariances of the various risk factors. If you recall from level 1, these are the formulas for the expected return and expected variance of a two-asset portfolio. So let's say these are the means and standard deviations of daily returns for the two stocks and their weights, and the covariance between them is 0.001. The mean annual portfolio return would be 9.2%, and the standard deviation is 8.9%. Note that these are based on annual returns. If we want one-day VaR, we would adjust the figures to their daily counterparts. Based on an assumption of 250 trading days in a year, the expected return is adjusted by dividing by 250, and the standard deviation is adjusted by dividing by the square root of 250. With the estimated mean and standard deviation of future return for the portfolio, and with the assumption of a normal distribution, estimating the 5% VaR is easy. That is, to determine this value where the area to the left is 5% of the distribution. If you look up the z-table and the z-score for 5% to the left is approximately minus 1.65, which means that this minimum loss is 1.65 standard deviations lower than the mean. Using the formula for z-statistic, we can solve for L, the minimum loss, which works out to 0.89%. In this case, we can state that the one-day 5% VaR of the portfolio is 0.89%. You should remember the z-value of minus 1.65, which is frequently used as it is the z-value of 5% VaR. For other probabilities, you may need to consult the z-table. Now's your turn to practice. Imagine you are the portfolio manager and you wish to find out the probability that the one-day loss is at least 1%. In this case, the value of L is minus 1%, and we want to determine the probability here. Let's calculate the Z statistic, which works out to minus 1.84. Look this up on the Z table, we get a corresponding probability of 3.3%. We can say that the probability that a loss of more than 1% on any given day is 3.3%. So, as you can see, the parametric method is relatively simple to apply under the assumption of normality. You should also note that the estimates of future return may not have to be strictly based on the historical data from the look-back period. And an analyst may make discretionary adjustments to such estimates, but of course the VAR estimated will only be as good as the inputs provided by the analyst. Besides, the VAR estimate is also very sensitive to the covariance estimate. Another shortcoming is that if the portfolio contains options, normality in returns cannot be reasonably assumed, so the parametric method has limited usefulness for portfolios with options. Next, the historical simulation method is based on the actual periodic changes in risk factors over the look-back period, so analysts are not allowed to make any discretionary adjustments. And unlike the parametric method, we do not characterize the distribution using the mean or standard deviation of return for each risk factor. Rather, we simulate the future daily return of the current portfolio given the daily historical changes in the risk factors over the look-back period, so the choice of look-back period is of importance for this method. The simulated returns are sorted from highest to the lowest. Once this is done, we can easily identify the largest 5% of losses. The smallest of those losses is our estimate of the 5% VAR for the current portfolio. One key advantage of this method is that we do not need to assume any kind of distribution of returns, and do not need to determine statistical estimates like mean and covariance. Also, the historical results will include changes in option values, if any, so the historical simulation method can be used to estimate the VAR for portfolios that include options. The shortcoming of this method is due to the strict use of unadjusted historical data, so the VAR estimate may be very sensitive to the choice of the look-back period. VAR based on an unusually volatile look-back period will yield overestimates of VAR. An analyst may be able to manipulate outcomes with a choice of look-back period that supports the desired outcome. The Monte Carlo simulation method may be able to address some of the shortcomings with the historical simulation method. Like the parametric method, the Monte Carlo method may reference data from a look-back period, but only to estimate the probability distribution for each risk factor. But unlike the parametric method, we do not need to consider the covariances between the various risk factors. Also, the assumed distributions need not be normal. Computer software is used to generate random values for each risk factor, and pricing models are used to calculate the change in portfolio value for that set of risk factor changes. The advantage here is that the pricing model can be configured to handle various types of securities. For example, complex options can be priced by simulating outcomes of the underlying, which are fed to an option pricing model to determine the value of the option. The simulation process is typically repeated thousands of times, generating plenty of return outcomes. Then, just as with historical simulation, we can order the outcomes and identify the lower fifth percentile to estimate the 5% VAR. If the distribution of the risk factors are all assumed normal, the distribution of the portfolio returns will approximate to normal if the number of iterations is sufficiently large, so the VAR estimate is likely to be quite close to the estimate from the parametric method. In summary, the parametric method requires the assumption of normal distribution of returns. As option returns cannot be modeled with a normal distribution, the method cannot handle certain securities like options. The analyst can make adjustments to statistical estimates, but that also means the VAR estimate is sensitive to the analyst's estimates of the mean and standard deviation of the risk factors and the covariances between them. Another disadvantage is that the modeling can get very complicated for portfolios with several securities and risk factors. In contrast, the historical simulation method makes no assumption on the distribution of each risk factor, as actual historical data are used as they are, so the method can handle options in the portfolio. Analyst adjustments are not possible as actual historical data is to be used. The VAR is particularly sensitive to the choice of look-back period, and as the method merely uses historical data as they are, it can handle portfolios with multiple securities and risk factors. Monte Carlo simulation does not need to be constrained by the assumption of normal distribution for the portfolio return. The risk factors may be modeled using any distribution, so the value of options may be modeled based on their underlying assets. Analysts are also allowed to make discretionary adjustments to the models if needed, but care should be taken to make the models accurate as the VaR estimate is particularly sensitive to the distribution assumptions. And like the historical simulation method, the Monte Carlo method can handle portfolios with several securities and risk factors, as there is no need to consider covariances. And that concludes this introductory lesson on the definition and methods of estimating value at risk. In our next lesson, we shall discuss the advantages and limitations, as well as other forms of VaR.